Hello, today's presentation is brought to you by Science Visualized. And today we're looking at how to write electron configuration. In order to do that, you follow three rules. The first one is called Aufbau Principle, which states that you start filling orbitals starting with the lowest energy first. So for example, you'll fill 1s, and then next 2s, like that. And we're going to see how to develop that diagram or that order for filling electrons. The second rule is called Pauli Exclusion Principle. And this states that if you have to put two electrons in the same orbital, they have to occupy it in what we call opposite spins. So for example, if that's an orbital and you have two electrons, then one electron will have the spin going up and the other one will have the spin going down, opposite spins, not parallel spins. The third rule is called Hund's rule. And this states that if you have degenerate orbitals, so degenerate means the same energy level. So for example, p orbitals, remember p orbital has px, py, and pz. So all of them have the same energy. Now, if you have one electron, so that's the number of electrons, and you want to fill these p orbitals, then they will all go, that one will just go into one of the orbitals. It doesn't matter whether it's px, py, pz, because they're equal in energy. If you have two electrons, then now you start filling them in parallel spins. That means they all face up or they both face down. As opposed to Pauli principle, where all of them are in the same orbital, that's the only time you have to pair them. If you have three electrons, then parallel spins until half full. So this is half full. All the three p orbitals are filled with one electron. Now, if you have four electrons, now again, you fill them in parallel until half full, and that's three electrons. Now we're left with one, and then you start pairing. So you put that one in the first orbital. Then if you have five electrons, again, you fill them until half full, that's three, and then you start pairing, and now we've accounted for five. And that's because there is a stability associated with half-filled orbitals. Now let's continue with our discussion on how to write the electron configuration. Now the first orbital that has the lowest energy is the 1s, and s is one orbital. Each orbital can be occupied by a maximum of 2, so it becomes 1s2. And then next you go to the second level, so that's 2s, 2, and then now you start the 2p. Remember, you have px, py, pz, each of them with a maximum of 2, making 6 electrons. Next, you go to the third level, 3s2, 3p6, and now you start the d orbitals, so 3d, but remember you have a total of 5d orbitals, each of them with a maximum of 2 electrons, making 10 electrons, 3d10. Next, 4s2, 4p6, 4d10, and then 5s2, 5p6, 5d10, 6s2, 6p6, 6d10. And for this video, we're only going to stop at d. We're not going to go into the next orbital, which is f and g. By the time you get to around here, you'll have covered most of the elements in the periodic table. So now, what's the order of filling electrons? The order is, you draw a diagonal line like that, so you start with 1s2, and then next 2s2, and then next 2p6, 3s2, and then next 3p6, 4s2, next 3d10, 4p6, 5s2, and then you can continue again with the next one. Now, if you're told to write the electron configuration of, say, sodium in the periodic table, you'll see that sodium is written as Na, and then you have 11 here, that's the atomic number, and you have 22.9, so that's about 23, and that's the atomic mass, and that's the atomic weight. So actually, what we need to focus on is this number 11, which is equal to Z, which equals to the number of protons, and for a neutral atom, that will be equal to the number of electrons. So that equals to 11 electrons. In order to write the electronic configuration for sodium, we have to distribute these 11 electrons following this order here. So we see that we're going to start with 1s2. So the electron configuration of that will be 1s2, 2s2, that makes 4 electrons, minus 11, we are left with 7. Next will be 2p6, so that's a total of 10 electrons, we are only left with 1. And then the next one will be 3s, and instead of writing 3s2, we'll write 3s1, so that we account for all the 11 electrons, and this will be the electronic configuration for sodium. Now, what about sodium ion, Na+? Na+, for you to form a positive charge, it means the sodium lost 1 electron, and therefore now the number of electrons equals to the original 11 for neutral sodium minus 1 electron, which equals to 10 electrons. And therefore we just have to distribute these 10 electrons following this order, and that will be 1s2, 2s2, 2p6, and there's nothing because that's already 10. So we have accounted for 10. Now there is another method for writing electronic configuration, and that's an abbreviated method. So you have an abbreviated method where we use what we call inert gas core structure. So you have the core structure, and if you look at sodium with 11 electrons and you look at the periodic table, you'll see that just before sodium you have neon, which has an atomic number of 10 and a mass of 20. So we see that we can actually write the electron configuration for sodium using the neon core structure, and because that accounts for 10 electrons, that means that will be up to here. So that will be 10 electrons. So that means the electron configuration for sodium will be, you write the neon core structure, which is actually 10 electrons, and then you're left with 1, and that one will be on 3s1. And then in this case, where you only have 10 electrons, the electron configuration for that can be just written as the neon core structure because they all have the 10 electrons, and that's called isoelectronic. That means they have the same number of electrons. So both sodium plus and neon are isoelectronic. Thank you very much. If you enjoyed this presentation, please support the channel by subscribing and also liking the video. Feel free to leave your comment below.